Okay, so yesterday we went over position versus time graphs. And of course, a position versus time graph tells us where an object is at any point in time recorded on the graph. Well, today we're going to look at the velocity versus time graphs, which tell us how fast and in what direction the object is going at any point in time recorded on the graph. Okay. So our first comparison here is going to be of two graphs. One of them is a position versus time graph. The other is a velocity versus time graph. Okay. Now, what are these two graphs showing? So this is a position versus time graph here on the left. Okay. We've got a diagonal line that is increasing over time. What is that showing us from yesterday? It's moving constantly at a constant velocity, right? Okay. We know that the position is changing at a constant rate over time. If that's the case, then this is an object moving at a constant velocity. What is this velocity versus time graph showing? It's something moving at a constant velocity. They look different because they're talking about the same motion from different points of view. This is showing the velocity, which is constant. Thus, it's not changing. Okay? But we immediately look at this and go, not moving, because we see a flat line. Okay? Flat line just means something is constant or not changing. In this case, it's not the position that's not changing, it's the velocity that's not changing. Now, was this a flat line at 0? Then we could say, yes, it's not moving. Okay? But in this case, it is moving, and it's moving at like 260 meters per second. Okay? Quite fast, in fact. Right? But it is moving at a constant velocity of 260 meters per second. Everybody follow me there? All right. Here's the mathematical proof that these things are both showing the same thing. Okay? Like exactly the same thing. If I look at this, and I want to calculate the velocity from this position versus time graph, okay? Velocity is displacement over time, or I could even do this, m equals y minus b over x. Either one of them will get me the right answer here. Okay, I'll just plug into here. I'm going to use this spot here as y, okay? And it's 1400. Okay, I'll use this as b, because it's where the y-intercept is. Okay, that's at 100. And this all takes 5 seconds. Okay, so 1300 over 5, pretty sure is 260. Okay, so this graph is showing an object traveling at a constant speed of constant velocity of 260 meters per second forward. This is showing an object traveling at a constant velocity of 260 meters per second forward. Okay, they're showing exactly the same thing. Everybody okay with that? Okay. How could I calculate the displacement of this object from this velocity versus time graph? Multiply the velocity with the time. I'd say that's a good idea. Because that is a manipulation of that formula. Agreed? Okay, so the velocity I can read off of the y-axis, it's 260, and it occurs for 5 seconds. What am I going to get here? Thinking back to this graph. What's 260 times 5? Is that not what we got right here for the change in position? Right, 1300? These two graphs are definitely showing us the same thing. Okay, what if instead of having that flat line, instead this graph looked like this? Now what's that object doing? It's speeding up over time. Its velocity is increasing. Okay, because we're seeing a line that started at 100 and ended at 400 meters per second. Okay, obviously the velocity of the object has increased, okay, over time. What do we call that if something's velocity is increasing over time? It's accelerating, right? What would that look like on this graph? Yeah, it would look like this, right? Okay, because our velocity would now be changing instead of staying constant, right? The line would be getting steeper and steeper. All right, now I've got this accelerating object. How could I calculate the acceleration? Or maybe, is there some part of the graph that we typically calculate that could represent the acceleration? Won't be the area underneath the line, because actually that's what we calculated displacement with just a minute ago, right? Because it's velocity times time, okay? What else could I calculate? Something we almost always calculate off of a linear graph like this. The slope. Okay? I mean, think about it. If acceleration is a change in velocity divided by time, finding the slope of this line would tell me the rate at which I change my velocity over time. Agreed? Okay? So back in Science 10, you learned this formula here. Okay? Acceleration is change in velocity divided by time. All right. The slope formula, okay, or the line, the graphing equation, okay, manipulated for m. Does it look similar? Okay. And since this is a velocity versus time graph, y is vf, b is vi, and x is time. Okay? That's where that formula comes from. Okay? It's the slope of the line on the velocity versus time graph. Again, it's not something I have to memorize. It's something I just worked out. Okay? I just looked at what was on the graph. I looked at the graphing equation and figured out, oh, the slope of this graph is acceleration. Okay? Everybody all right with that? Okay. So on this graph then, okay, we would go 400 minus 100. Okay, those are our two numbers there. Okay, and that took 4 seconds. Okay, so 300 over 4 will give us our rate of acceleration. All right, so our acceleration is 75 meters per second squared. Yeah, remember units for acceleration are meters per second, or meters per second squared, right? It's how quickly you're changing your meters per second. All right, is that pretty fast? It is. Okay, remember, if you were to fall, you would accelerate at 9.81 meters per second. This is accelerating at 75 meters per second. Okay, if we do this, that means you would be pulling 7.6 Gs. And if you guys know what G-force means, you would feel 7.6 times heavier than normal. In other words, you would very quickly black out, because the blood would not be able to be pumped to your brain, and the brain would starve from oxygen deprivation and pass out. All right, last thing. Okay, now we just said a minute ago that, whoa, that's not what I wanted. Okay, we just said a minute ago that if we calculated the area under the line on this graph, it calculated displacement. Everybody's okay with that? Okay, and when we did that, what we were really doing was saying that displacement equals average velocity times time. Can I still do that if the object is accelerating uniformly like this? I can. Okay, can I find the area of a triangle? How do I do it? Base times height over 2. Okay, so base times height over 2. Okay, this thing accelerates from 100 to 400 meters per second. Its average velocity, which is what I need here, is halfway in between 100 and 400. Would you agree? Is Is that the height of the triangle divided by 2? Okay, that's where we get that from. Okay, that's why finding the area of that triangle works. The area of that triangle is taking the average velocity and multiplying by the base, which is time. Okay, that's why finding the area under the triangle or under the line represents displacement. Okay, again, it's not something I need to memorize. It's something I can figure out from my graph, okay, just by looking at it. Okay, is that ringing a bell? Okay, probably second semester, not so much. Second semester science 10, probably not so much. But first semester, certainly we spent a fair amount of time on that. Okay, what is this velocity versus time graph? Okay, so it says here, how would you describe the runner's velocity? So what is the runner's velocity doing here in this first part? It's accelerating, yeah. The velocity is increasing in the first part, okay? So if this is like, you know, a race, okay, and they've just fired the starter's pistol, okay, this is when they jump out of the blocks and they're accelerating, okay? Now when you're running a race, okay, and you're accelerating, you can only run up until you hit your top speed. And at that point, it doesn't matter how much harder you pull, you're not gonna run any faster, okay? The force of air resistance and the force you can apply to the track become balanced and you simply can't run any faster. So you will run at your top speed after that, which is what's going on right here. The velocity doesn't change anymore because they simply can't run any faster, okay? What's happening here in this last part? They're slowing down, right? So they probably crossed the finish line, okay? And now they're slowing down. Do they actually stop? Does their velocity become 0? Then they actually stop, okay? Right here, at like 14 seconds, okay, their velocity becomes 0, okay? And I can see for a few of you, like, wait a minute, it doesn't seem right, okay? But I think what's happening is a lot of us are still picturing this like it's a position versus time graph. Every time we look at a graph, we've got to make sure we know what kind we're looking at. And on an exam or a quiz, that's the most common mistake people make. They don't look carefully at what kind of graph they're dealing with, and they do the wrong operations for that graph, okay? Which tells me they were the people who memorized what was what on the graph, instead of looking at the graph and analyzing, okay? So that's the disadvantage of the memorizing part, is we just want to go to what we memorized, as opposed to looking at the graph and figuring out what's on it, okay? All right. So for velocity versus time graphs, okay, if we're reading off of a velocity versus time graph, then obviously we can read the velocity, instantaneous velocity, at any point in time, because that's what the graph directly shows us, okay? And we can calculate, okay, the area underneath the line to be equal to the displacement, okay? And we talked about why that was, okay? Because displacement equals average velocity multiplied by time, so that's effectively base times height, or sorry, base times height, okay, or base times height over 2 if it's an accelerating object, okay, and the slope obviously on this graph is equal to acceleration, because acceleration is the change in velocity over time, okay, and so that's where we get, sorry. Okay, that's where we get that from. All right, so just analysis of the graph. All right, questions on any of that velocity versus time stuff? Okay, because hopefully that's reviewed. Okay, so you got this question here about a snowmobile. It's actually it's in your digital workbook. Okay, it's question 6, I think it's on like page 5 or something. I'll call it up here in a minute. Okay, snowmobile moves according to the velocity versus time graph that we have there. Okay, what is the snowmobile's average velocity during each of the segments? Okay, and then overall. So that's something we haven't talked about yet. So let's just quickly look at how we get the average velocity for each section. Okay, in this first part here, what's happening to the velocity? Yeah, it's increasing, right? It's accelerating here, okay? And it accelerates from 0 to 40 uniformly, okay? So its average velocity during that time will be what? It goes from 0 to 40 half the time it's going slower than 20, and half the time it's going faster than 20. So 20 is its average in the middle there. Okay, it's accelerating uniformly, okay, from 0 to 40 meters per second. Okay, so the average is actually the halfway point. Okay, that's where that whole base times height over 2 thing came in, right, when we were calculating the displacement. Question?
What's the unit of time?
Seconds. So meters per second here, seconds here. Okay?
It says hours, not
Weird. Okay, well, let's make it match. It's probably because I redid the graph because it was ugly and I went to the wrong units. So I'll take responsibility for that one. Okay, during the second part here, this flat part, okay, what's happening there? Moving at a constant velocity of 40 meters per second. So what's the average velocity during that part? 40 kilometers per hour. Okay. And in this last part, the object accelerates again. It accelerates from 40 to 80 meters per second. So what's the average velocity between these 2 points? 60. Yeah. Okay. Half the time it's going slower than 60, half the time it's going faster than 60, so 60 would be the average. And again, that's where that whole base times height over 2 thing comes from. That's time multiplied by average velocity. Okay, that's giving us our displacement, okay, when we're calculating the area. Okay, so we did A, B, and C, okay? I want you to calculate the average velocity over the whole trip. What 2 things do you need for that? Total displacement and total time. Well, you have total time, it's 60 hours, okay? We need to get the displacement. And I think you guys know how to get displacement off a velocity versus time graph. You might have to break it up into a few different shapes, okay? So I think you guys can get that. So I'll give you a few minutes on that, and then we'll walk through it together. Okay, so if we're going to calculate the average velocity, we need the total displacement and the total time, okay? So what we need to use then is the average velocity and the times in order to get the total displacement of the object snowmobile in this particular question. All right, so that essentially then means I'm going to calculate the area of this triangle, this rectangle, and this triangle here, okay? The part people forget is the end of that rectangle usually, okay? They forget that I have to calculate the area between the line and the x-axis, including stuff that kind of looks like it's not part of it, okay? All right, so I've got this first triangle where the object is accelerating, okay? And we already established that its average velocity was 20 kilometers per hour during that first 20 hours, okay? So we're gonna have base times height over 2, so it'll be 40 over 2, which is 20 times 20. Okay, so this area here is going to be 400 kilometers. Are you all right with that? Okay. Then I've got this rectangle where essentially it travels at a constant velocity of 40 meters per second from 20 to 60 seconds. So 40 times 40, okay, that should be 1,600. Kilometers, is that right? Yeah. And then I've got this small triangle up here at the top, okay, where it's accelerating again. Okay, its average velocity is going to be 60. Okay, that happens for 10 hours, so 60 times 10. Okay, this is going to be 600 there. Okay. All right. So now that we're looking at these, we want to add them together. Okay, so this will be 2,600 meters, okay, and we're dividing that by the time, which is 60 hours. Okay, does that come out to 37.3? Doesn't feel like it. Do I have a mistake on there? 43. Okay, I don't know why I have 37.3. Okay, everybody all right with that one?
How did you get 600 for the triangle?
Oh, that's where I went wrong. The height of the triangle is not 600. It's not a doofus. The height of the triangle is 40, so this should be 20. This should be only 200. That's why. Good eye. Good eye. All right, so that's gonna mean this is gonna be 2,400, not 2,600. That's why it didn't seem right. Okay, 2,400, now that should be 37.3 kilometers per hour. Okay, sorry. Okay, everybody all right with that? Besides my screw up, that's a bad example. All right, so a couple of good kind of situational graphing questions here. Okay, at the end of a school day, student A and student B say goodbye and head in opposite directions, walking at constant rates. Student B heads west to the bus stop, while student A walks east to her house. After 3 minutes, student A is 300 meters east and student B is 450 meters west. Okay, so a position versus time graph of that movement is going to look like this, right? Student A walked east, but they didn't walk as fast, so their line's not as steep. Student B walked west, okay, so their line's a little steeper because they went a little bit further. Okay, determine the velocity in meters per second of each student. Well, okay, determining velocity simply means taking total displacement and dividing by total time. Okay, so we take their 450 divided by 3 minutes and we get their speeds in meters per minute. Okay, all right. Okay, we talked about how an object that is slowing down is going to have a graph that is a flattening curve on a position versus time graph. Okay, and we talked about that because obviously if they're slowing down, they're not covering as much distance every second. So like in this first second, they cover that much distance, but in the next second, that line's not nearly as long. Second after that, even shorter. Okay, and then here they're practically stopped. Okay, so we're getting less and less, so we get that curved line for the position time graph. Okay, I want you guys to try that one. Okay, the other formula you need for this is this. So when they're asking you to calculate acceleration, okay, that one's on your formula sheet, but okay, A equals VF minus VI over T. The other thing you have to calculate is the displacements. Right? So I'm going to give you a couple minutes on that one and see how you do it. So first off, if I want to calculate the displacement, okay, I need to recognize what kind of motions are going on in each part of the graph. Okay, this first part of the graph here, from 0 to 4 seconds, the object is doing what? Moving at a constant velocity of 3 meters per second east. Okay, so if I want to calculate the displacement for that part, I just have to go v times t, right? D equals v times t, so that's 3 times 4, so that's 12 meters east. Okay, then I've got this part of the graph here where the object is accelerating, so that's kind of a separate triangle, okay, that I would need to use the average velocity of. And then in here, okay, I could just get the area of this triangle here to get my last bit. So for this part here, so we're looking at that the height of this triangle is 2, right? It goes from 3 to 1, okay? The base of the triangle is 1, so basically it's 1 over 1, so this is going to be 1 meter east, okay? All right with that? Okay. And then we got this rectangle here at the bottom. We know the height of it is 1, and the base of it is 6, so this will be 6 meters east. All right, so we got 19 meters east, I think.
Is it time in minutes though? Yeah.
To make our life easier. I don't know why. I hate it when they put graphs there in minutes. Okay, doesn't make any sense. Sorry, did you already convert it all to seconds and do all that extra work?
Yes.
Okay. You know what? I should do it the way they do it. So we'll just erase these numbers here. Okay. So for this one, we'll have 3 times 300, no. Alright, so that's 720 meters, is that better? If you did it the right way, the way I should have done it, because I should have looked. Okay, 720, okay, this is going to be 60 seconds here, okay, so that'll be 60 meters in there, okay, and then 360 times, so this will be 360. Yeah? I shouldn't do stuff in my head, but I think that's where we're at. Okay, so 720, 60 plus 360, 1,140 meters east. Okay, then we got to calculate the acceleration, okay, and we could do this in meters per second per minute if we wanted to. It's a silly unit, but that's what we're given, okay. So if we're going to go and use this formula, we're going to have over the whole trip, it accelerates from 3 meters per second to 1 meter per second. So that's going to be 1 meter per second minus 3 meters per second over 10 minutes. So it's not a very big acceleration if it's in meters per second per minute. Okay, so we got 0.2 okay. Meters per second per minute. Okay, just like, terrible units, but that's what we got. All right. Okay, this is a really good one because I always have a question like this on our unit exam. Okay, bird starts flying south. Okay, we got a velocity versus time graph of this bird. And we can see that initially it is flying south here in part A. Its motion is described here. So from the graph, determine whether the acceleration is positive, negative, or 0 for each section. All right, in section A, is the acceleration positive, negative, or 0? It's negative. Its velocity is becoming more negative. Okay, it's speeding up south. All right, what about B? Positive, negative, or 0? 0. It's not accelerating here in part B. It's traveling at a constant velocity of 4 meters per second south. What about part C? If the acceleration is negative, it accelerates from -4 to -6 meters per second, or 4 meters per second south to 6 meters per second south. Okay, what's the acceleration in part D? 0, right? It's not accelerating. It's at a constant velocity of 6 meters per second south. What about in part E? Okay, is the acceleration positive, negative, or 0? Which way does the line go? It goes up, right? Okay, so what the bird is doing is it's accelerating in which direction? Its velocity is becoming more and more north over the course of this, right? It's going 6 meters per second south, and then 4 meters per second south, then 2 meters per second south, okay, and so on, and eventually it's going north at 6 meters per second, right? So it's definitely accelerating north, okay? It probably just turned around, okay? That's all it's doing, okay? All right, and then for part F, is the acceleration positive, negative, or 0? 0. It's traveling at a constant velocity of 6 meters per second north. Okay. So find the value of the acceleration where it is not 0. Okay, well that means using this formula here. A equals VF minus VI over T. So for part A, that's 4 minus 2 over 1. Okay, so that'll be -2 meters per second south. Meters per second, sorry, meters per second squared. Okay, here it's 0. Okay, for C, we go from 3 to 4, so another one where, okay, sorry, 3 seconds to 4 seconds, I think. Yeah, okay, so it's the same acceleration as here. How can I tell without doing any math that the accelerations here are the same? Remember, on this graph, the change in velocity over time is the slope. Are the slopes of those two lines the same? Okay, then I don't need to calculate it twice. I can visually tell that the accelerations are the same there. Okay, for this part here, okay, we plug into that formula, positive 6 minus negative 6, so that's 12, and that's over 3 seconds, I think. Okay, over 3 seconds, so that'll be 4 meters per second squared north, okay, for that part. Okay, part C is the tricky part. When does the bird change direction? Part of this graph, the bird is flying south. Part of this graph, the bird is flying north. At what time does it actually start flying north? 8.5 seconds? Yes. First time anybody has got that right on the first try. How many of you were thinking it was here? You don't have to admit it, but probably a lot of you were, okay? Because our gut reaction is, well, that's when the line starts going positively, so that must be when the bird changes direction. Except on this graph, we're seeing that the bird is still flying at -6 meters per second, -4 meters per second, -2 meters per second. It's still flying backwards until it gets to this point here. That's when the velocity is 0, and after that, the velocity is positive. Okay? So it's actually at this point here that the bird actually starts to change direction. Okay? So that graph is the same. It looks the same as a velocity versus time graph of throwing something up in the air. Okay? If I throw something up in the air, okay, the moment it leaves my hand, the graph will look like this. Because as soon as it leaves my hand, what is it doing? Well, it's moving up, but the whole time, it's accelerating down. Okay, if I throw something up in the air, the second it leaves my hand, the only force acting on it is gravity. So as soon as it leaves my hand, it's accelerating downwards at 9.8 meters per second. But it's still moving upwards until it gets to its highest point, which occurs right there, which is where it stops instantaneously, and then actually begins to fall back down. So something can accelerate down while moving up. It just means it's going slower and slower and slower. Everybody all right with that idea? It's a little weird when you first think about it, but then it should start to make sense. Okay. Or that. Or that. There's the one I want. We just did the snowmobile one. Okay, come on. Ah.